Yep. Oh, sure.
So I think we're going now. If you can't hear me, then speak up. But tonight I'll be talking a little bit about a very unique rock called Trinitite and a little bit of the history of how it was made. And I say made because Trinitite is a human-made glass and is a byproduct of nuclear testing. And more specifically, Trinitite was created in 1945 from just two ingredients, sand and heat. And it's a glass, and the source material was the Arcosic quartz-dominated sand from the White Sands Missile Ground testing grounds northwest of Alamogordo, New Mexico. The picture on the left there is from just outside the White Sands area, lots of light-colored sand, pretty familiar for kind of up close in the White Bluff area. But the amateur baker will have a little more difficulty in acquiring the necessary heat because that was provided by a nuclear explosion. But there you go, that's all you need to create your own Trinitite at home. But a little bit of an oversimplification and technically untrue because besides being wildly illegal to set off your own nuclear device, setting off your own personal nuclear bomb in a sandy desert won't create Trinitite. You'll create glass and an international incident, but it still won't be Trinitite. All of the Trinitite that is or ever shall be created was made in one fell swoop on the morning of July 16th, 1945, during the world's first full-scale test of a plutonium nuclear bomb. And it was connected at the Trinity Test site, hence the name Trinitite, in the northern portion of the White Sands missile range here. And plutonium for the core of the bomb was refined up the road at Hanford, which I thought was why it might be of interest to some of you. And some have called it the start of the nuclear age. The code name for the test bomb was the Gadget. Pictured here, half assembled with future Los Alamos National Lab Director Norris Bradbury. And it was an implosion-designed plutonium bomb in which a solid core of plutonium-gallium hybrid is surrounded by explosives. And then when the explosives are detonated, the compression creates a supercriticality, which in turn initiates the nuclear fission chain reaction. And the Gadget used the same fission mechanism as Fat Man, which was detonated over Nagasaki. And the other design, utilizing the aptly named gun method, has explosives that accelerate a piece of fissionable material into each other to initiate that chain reaction. And that was what was used in Little Boy. So there's these two designs, but only the implosion method was tested at full scale before it was used in warfare. And this was July 16th, 1945. We were still at war. It was going on for quite a while. And America wound up using Little Boy and Fat Man less than a month after the test. But the reason they didn't do a full-scale test of the Little Boy gun method was because they had tested every other aspect except for using live material. And they were just so absolutely certain it was going to work that they didn't want to waste the material, essentially. But this design was a little more radical, I guess. And the assembled Gadget was hauled up to the top of a 30-meter tower in the White Sands missile range, and the bomb was detonated at elevation for several reasons. One, it better simulated the effect of dropping the bomb from a plane. It also reduced fallout by lessening the amount of ground material that got swept up in the blast. And it helped maximize the amount of heat directed at the ground. And so with these components in place, we have the Trinity Test. This is a video from the Los Alamos National Laboratory Archives of the test, which was witnessed by around 425 military and research staff from the Manhattan Project. And many people from the neighboring town saw the flash of light and the distant boom, but they were lied to about what it actually was at the time, saying it was some gun factory exploded or various other excuses. And this effort was led, of course, by Robert Oppenheimer, who would later recall, in part, we knew the world would not be the same. A few people laughed, a few people cried. Most people were silent. And from the Bhagavad Gita, he thought of the line, "Now I am become death, the destroyer of worlds." And now if you didn't before, you know that this quote has its origin, or it's linked to Trinitite and the Trinity Test on July 16th. And it actually took me a while to make that connection of that famous quote to this little glass material that I actually studied in research. And the Trinity Test was, of course, well studied, or it wouldn't have been a very useful test. They used all sorts of high-speed cameras, plenty of radiation detection and explosive monitoring equipment around the site. And from the measurements, we know, for example, that the fireball reached temperatures of about 8,000 degrees Celsius and had about a 22 kiloton yield. And in the center there is the only color photograph of the test. They were so focused on high speed and quality images that they didn't use any color photography, except for this one person who, it might have been a press guy, I can't remember who took the actual photo. But in the aftermath of the explosion, the world was obviously changed forever. And the first thing to change was actually the state of the gadget and the blast tower, which were both completely vaporized. And in the photo on the left, it's a few weeks after the blast. That's Oppenheimer on the left and General Groves, who is a major leader in the project, that were inspecting a piece of the tower. And all that's left is just some ground supports. The area was, of course, slightly radioactive still, but actually surprisingly not at a dangerous level for just short exposure times for through the skin. But it may be hard to tell, but General Groves, and his feet are hidden, but he has little white booties on over his shoes to prevent radioactive material from sticking to his feet. And on the right, flyover imagery shortly after the blast, and this one is from 28 hours after the blast, shows very, very clearly this dark region, which is approximately 450 meter diameter dark patch. And all of that is Trinitite. And so I'm telling you this story of all the background because all of that was incorporated into Trinitite. And so the desert sand was arcosic. This means that it was mostly quartz, but has a substantial amount of feldspar, in this case, microcline and albite, with lesser amounts of muscovite, actinolite, calcite, some amphibole. And one important aspect of the Trinitite creation is that the desert sand wasn't just baked in place. There was the heat wave that melted some of the surface, but recent research in the last couple of decades has shown that the glassy Trinitite was actually created as fallout after the explosion. So that means instead of being baked like a desert cake, the material was evaporated just like the tower and swept up into the fireball and later rained out as glassy droplets that coalesced to form a solid sheet of glass on the desert floor. And so this Trinity Test photo on the bottom right is from 0.09 seconds, less than 1/10 of a second after detonation. And I think this shows it really well, where you focus on the fireball at first, but what I wanted to point out is this dark ring around the base here, where what's happening is that the heat and the shock wave is sweeping up the desert sand. So you get these little eddies of sand and melt glass and all that stuff getting swept up that'll get raised up into the mushroom cloud before it gets chaotically mixed together and then vaporized and rained back down. And so then it all rains back down and cools into Trinitite. And Trinitite has a number of, I think, cool and somewhat unique features and characteristics. One of the more obvious is, most of the samples, there's a green coloration, which if you think about it, it started out as this definitely not green sand, but the green is due to iron, and I think specifically to iron 2+ in the glass, as it was in a reducing environment when it melted and was incorporated. And another feature is the often smooth surface. This is the top of a piece, and it's very smooth apart from vesicles. And this surface is described as having a mosaic or craquelure texture to it. And so, like I said, another characteristic is the vesicles. where this glass was superheated as it was being deposited, and the desert was relatively cooler and had a bit of water in it. And so the heat boiled off water and other volatiles, creating a range of bubble sizes in the samples, many of which were frozen in place in the subsurface. So you can see quite a few vesicles, and here there's a little one under this blob of iron. I think I'll come back to a slide similar to this later. And so these varieties here are the most common types, which is just called green trinitite. And these are from the Notre Dame research collection material that I used in my research. And the top two photos are actually of the same sample, where we have the top on the left and the sandy underside on the bottom, where it didn't actually quite melt everything. And it's sort of held together by some of the glass that percolated down into the sandy material. And once you get familiar with trinitite, it really becomes easy to tell which way it was originally up. Essentially look for the smooth glassy layer. So we have the top here and then these two undersides, and you have some very large vesicles here. And these are inches in the background. And there are a few other less common trinitite types, and these include red trinitite, which is due to copper, primarily from the wiring in the bomb. And so you can actually trace the different anthropogenic contributors to the different colors in the trinitite. So this is a rare and valuable piece from Trinitite Man via Twitter. There's also black trinitite, which has lots of iron, mostly from the tower. And I've said the tower was vaporized in the blast, and it had to go somewhere. And so it was a lot of it recoalesced and precipitated out. The sample photo from Twitter has an actual blob of iron just sitting right there under the surface. So it sunk down into the glass. And the sample with the red triangle here is pointing to some of the red streaks along where my cursor is now, along showing from the copper. There's also beads and dumbbell shapes of trinitite, which formed as the molten glass coalesced in the air and cooled just enough to hold their shape as they spun, or either as spheres, or if they spun out fast enough, then they would get elongated and form these dumbbell shapes. And so the Manhattan Project scientists did their best to collect as much information as they could from the blast, but we're still learning new things about trinitite and Trinity decades later. And the reason I'm familiar is because of a postdoc I had at the University of Notre Dame, where trinitite was being studied because of its use in nuclear forensics. So I've spent a lot of time looking specifically at trinitite thin sections, where we take a slice of rock and plane it down to just a few tens of microns in thickness. So the minerals are transparent, which is what's at the bottom here. This is from this sample here, from the top and the bottom. And this is a composite image of that thin section. And you can see there is, even in thin section, there's this smooth top and then a lot more broken up at the bottom with a lot more vesicles as you go further down, because they got trapped underneath the surface of the quenching top layer. And it also looks dirtier at the bottom because there's less glass, and so there's more opaque minerals and original unmelted minerals at the bottom. And for example, I took that a step further, and one of our goals is to figure out, where everything was inside these samples. And one of the techniques we used is a thing called micro X-ray fluorescence imaging to get the distribution of individual elements in the section. So these were mapped on a spectrometer. And we can use these maps to do targeted analyses. And so if you want to research the blast effects on quartz, well, you look at a silica map and on the lower left here, and the brightest regions are quartz, since that's just silica oxide. And if you want to look at feldspars, there's the potassium and aluminum maps. So potassium here, that would be potassium feldspar. Calcite would be in the calcium map. And if you're looking for exotic components like the tower or bomb material, maybe you would look at iron or the copper. That would show you areas of interest. So we have quite a bit of iron at the bottom and then a very bright region at the top. And so in terms of sample characteristics, the last thing I want to point out is that trinitite remain slightly radioactive today. The levels today are safe enough to where you can, if you wanted, handle most pieces with your bare hands, but it's still there. And for nuclear forensic purposes, are interested in knowing, exactly where this radioactivity is and how it was distributed in the samples. And the way we do that is there's a resin that you put over thin sections that's sensitive to alpha particles. And so other students at Notre Dame did this and conducted alpha track radiography is the technique of all the thin sections that we looked at. And this, tape the resin to the thin section, wait a few days, and then digitize the result in tracks, which are shown here in red. And the results for this particular sample are overlain in the red, where each tiny red dot is an alpha track. And you might think at first that there's 5 or so bright regions, but those are actually clusters of hundreds, if not thousands, of small red alpha particle tracks. And a lot of it is very diffuse, but there are 2 key takeaways. One is that there is a lot of alpha track radiation scattered throughout the sample, even down by the majority unmelted grains. And it's hard to tell, but it is only in the glassy regions where it is concentrated in the sample. And so that's the material that was brought up into the fire blast, all the other radioactive material. And this was, so there's, residual plutonium decaying in there. And the other more obvious characteristic is that there are very highly concentrated regions of alpha activity right at the surface. And the levels are, I think, well below background, but I would still not advise you to wear Trinitite jewelry. And yes, that is a thing. Maybe not these days, but it was a thing. In part, I think that, was it government sponsored? Somebody sponsored it to show how safe nuclear energy was. And so they made these earrings out of it. And the most dangerous thing you could do, however, is accidentally swallow some Trinitite, because then even the weak alpha radioactivity, which generally can't even get past your skin, it would be inside you, and so it would start interacting directly with your tissues, which exponentially increases the potential for cancerous growth. And so if you're dealing with Trinitite, definitely wash your hands afterward. And there are many other avenues of research being undertaken with Trinitite. I won't do a lot of detail here, but these 3 examples came out of Notre Dame. They showed that you could roughly tell how far from ground zero a sample was collected based on the decay products in those samples, notably 152 europium. So as you get less 152 europium, you're more likely to be further away from the center of the tower. So if you had the sample, you could identify, how many meters away from the tower it was potentially, because there would have been less neutron flux further from the tower. And the source of materials from the bomb is also an important avenue of research where we can use, for example, zinc as a proxy for copper. We can tell that the wiring and other copper material in the bomb came from a mixture of 2 mines from Michigan and Utah. And the lead isotope signature is also best matched by a Canadian industrial mine in Buchan's up in Canada. And so these types of signatures are important because if something were to happen in the future, or even if a bomb was intercepted or even just radioactive material, then we want to know where the material came from to determine who the bad actors were in that, getting that out there into the wild. And so speaking of dealing with Trinitite, where might you go to do that? For years after the Trinity Test, lots of reporters and tourists were able to just visit the site, and it was essentially a free-for-all if anyone wanted to take a piece. I found an account of someone just taking a shovel and a sifter and just digging up the surface and loading it into the back of their pickup truck to take home. And yes, so there are kinds of people bring shovels. Ostensibly, out of concern for latent radioactivity, the collection of Trinitite was banned in 1952, and everything on the market was collected before 1953, which is all completely legal to trade. And to reduce the environmental hazards of Trinitite just laying around on the surface, the government bulldozed the Trinity site and buried all the rest of the material, or I did read from one source that they kept a small surface exposure visible, so tourists could see what the ground originally looked like after the blast. But I haven't been to the site myself, so I can't say if that's the case. So if you've happened to visit New Mexico, especially around the White Sands Missile Range, you'll probably find a lot of trinitite for sale, which is variably called adamsite and Alamogordo glass as well. And I think it's a staple for a lot of mineral dealers as well, because it's kind of a neat piece of history to have. And I'm not sure how prevalent fakes are, but like with all things rare, there are some trinitite scams out there. If you know what to look for, I think you'll be okay. But honestly, the only way to be 100% sure you have the real thing is to do a spectroscopic or radiography investigation of the samples, like the one shown here with the decay byproducts. Europium 152 again shows up where they're still evident, and it's characteristic of the Trinity test as opposed to other post-nuclear detonation material, or even just other randomly spiked material. And even if you had a Geiger counter, you could say it's radioactive, but a sophisticated operation could potentially implant small, naturally radioactive materials in there to fool you. So unless you know what was actually radioactive in the material, you wouldn't be able to tell. And it's an opinion, but I don't think authentic trinitite is terribly expensive, but you'd kind of have to judge for yourself. As an example of typical costs, this sample on the right is from the Mineralogical Research Company, which is where all of our material at Notre Dame was purchased from. It's a little over an inch long and an inch wide, and it costs $35. So about 8 to 10 grams, $8 to $10 per gram isn't unusual. And rarer, larger, and more unusual samples, like with copper or iron, they'll obviously be pricier. And those are often upwards of about $15 per gram, at least from the Mineralogical Society or Mineralogical Research Company. And the most expensive piece on their site right now is about $107 which is a piece about twice this size, so a couple inches in diameter. But you also have to remember that trinitite, when you're looking at trinitite, you have to remember that it was formed as a surface layer deposit, and so it isn't very thick. Most samples aren't more than about 1 to 4 inches across because it's kind of crumbly, it breaks apart when people collected it. And some places sell just little vials of small pieces for less than about $15, so you get lots of random small pieces in there. And larger ones like this are around a 5-inch vial from the Atomic Rock Shop for $60. But if you find someone selling a basketball-sized piece, just walk away. On the right, I found this supposed trinitite for sale for $65,000 on a knockoff eBay site. And I can't say definitively that it's a scam without actually seeing it, but it's just a scam. It really doesn't look like trinitite to me. It's very solid. There's no vesicles. It's more blue-green than green. There's no photos of the other side, so you can't tell if there's a glassy or sandy side. And it's extremely thick. That's somebody's hand for scale there. It's definitely, probably 6 inches deep, which is just ridiculous for trinitite. But I guess, when you go all in like this on your scan, you only need one to make a fortune. So my guess is that might be aventurine, which is just a variety of quartz. So, you get a pretty good return if you sell one. There are some other just natural lookalikes that aren't necessarily scams, but you got to be careful if you're out there collecting. These might be mislabeled or tried to pass off as trinitite. Glass slag is one example. Fulgurites are probably the closest match, which are the lightning strikes, which has a similar, brief high temperature burst of energy in sand, which forms, green glassy vesicular surface with kind of a smooth or vesicular interior with a smooth surface. But compared to trinitite below, they're both kind of tube-shaped and green vesicles, but fulgurite is darker on the surface, whereas trinitite is still green on the surface. We got this dark kind of gray surface on the fulgurite. And the trinitite is just a single layer of unmelted sand grains, whereas tektites, they're coated with them. But if this was broken in half, it might be harder to tell that this was fulgurite versus trinitite. Tektites are another possibility. They're green glass formed by meteor impacts or air bursts above desert sands, but those glasses tend to be clearer and bigger and chunkier, and I don't know that they necessarily have the same kind of desert sand attached to them usually. They typically tend to be clean from what I've seen. So finally, I thought I'd wrap up by showing you what I can of my Trinitite collection, which I didn't even know I had for quite a while. My grandfather died shortly after I was born, and I eventually inherited his rock collection, but very few of his samples had identifying labels or sources, which kind of goes back to Larry's talk a while ago about labeling your rocks so people know what they are. But back in 2010, I photographed what I thought was a couple of interesting green rocks, and I sorted through them later. And I didn't know what these were at the time, but it wasn't until I studied them almost a decade later that just by, and I didn't study them until a decade later, so I didn't even know Trinitite was a thing for a long time. But just by coincidence, last summer I was scrolling through old photos and found this one of these samples showing, this very familiar now green vesicular glassy samples with the crecular texture on the top, some rents and vesicles. And this is the only photo I took. So unfortunately, I don't know what the underside of these samples looks like. And the bulk of my rock collection is back in New York, which is where it's been stashed while I've moved around. So I still got to figure out how to move a rock collection across the country in a pandemic. But until then, I think all I can say is that these are strong candidates for being Trinitite because they have the characteristics I talked about earlier. And there might be some sandiness at the bottom there that might have flaked off, and hopefully I wash my hands after I touch these. But I'd be interested to know if anyone else has any samples of Trinitite or has visited the Trinity area before. And apart from that, I'll take any questions you might have.
This is Jerry Johnson. Question. Being that's green glass, there's got to be a lot of small gas bubbles within the glass. Has anybody ever tried to analyze the contents of the gas?
Oh, the gas.
In other words, you could take a sample of this, you could melt it, you could have an evacuated chamber, you could catch the gas, you could use a carrier gas, and you could run it through a GCMS.
Yeah, I'm trying to think if I read about any of that. I can't think of a study offhand, but
just
yes,
curious.
that would definitely be a possibility.
I was just wondering, if the gas bubbles would detect something very unusual as a result of the atomic blast.
Yeah, if they form, somewhere at the surface, especially. Right. What the atmosphere of a nuclear detonation would be like in that moment in time.
Toxic. Hey, Patrick, how would you store something like that if you had something if you had a small collection of that? Just a glass bottle or?
Yeah, I think just a glass bottle is fine. It's the type of radiation that can't even penetrate your skin, really. So just like a piece of paper is essentially enough to stop it.
Okay.
How much longer is it going to be radioactive?
It's already below essentially background levels of certainly less than a banana. So
that's because of potassium 40.
Yeah.
Banana, you could take some of those Lowry seasoned salt. Someone had that once out in the lab building I was at, and they set off a Geiger counter with the Lowry seasoned salt.
And I showed the decay scheme for 152 europium a while ago. Where was that? It was in this chart here. So the activity of that decay product is, less than a fifth of what it was a long time ago now, 80 years ago. So it'll be slightly radioactive for almost indefinitely, but detection wise, I'm not sure how long you'll be able to detect it.
So I have a couple pieces. I don't know if you can see them. I've mounted them in a Riker box, and I do that because they're slightly friable. And I did run a Geiger counter over them, and I forget what it was, but it wasn't a lot. It was less than like 5 millirem per hour. It was pretty negligible. So I don't know if people can see it, but that's kind of how I deal with it. So put it in a Riker mount, and then you just don't basically deal with it because it is kind of crumbly, and it does kind of peel off.
Yeah, we had that issue with sand coming off the bottom as we handled it. So we had to, work with it over paper and collect it at the end, so it didn't get in the laboratory anywhere.
Yeah.
What is it? 10 half-lives? That's a rule of thumb. And then not radioactive.
Yeah, I think that sounds about right.
Hey, Bill,
Yeah.
has your plastic case on your Riker mount melted or deformed?
No, actually, it's pretty cool. It's pretty well air conditioned. It's I feel fine. The third eye that I have is barely noticeable.
But he glows in the dark.
Yeah.
Chemistry.
Yeah, it's all good, man. Any other questions for Patrick? That was a really good presentation.
Let's put up the pretty photos one last time.
Hey,
You have a-
remind me of peridot. Any similarities?
No,
I missed the first part of that question, but it sounds like Jerry answered it.
I doubt it.
It was similarity to peridot.
Oh yeah.
No. Compositions could be quite a bit different.
So, do you have a piece of the actual red trinitite material, or have you ever seen one? I know there's a picture of it here, but it really I've never seen one personally, only pictures.
Not to this level of redness, no. We just had some with a few small inclusions in it that were, red or blue or white, but nothing this broad scale.
Hey,
Yeah.
Bill, show your case and everybody pin his video so then you can see. If you pin his video, then you can see a bigger
You want me to
screen.
stop sharing?
You can stop sharing. That can help a little bit too.
I don't know if people can see it.
If you do the 3 dots and then hit pin Bill's picture, you can get his to show up larger.
Yeah, it works.
It looks a lot like mine too.
Yeah, just a couple pieces. I picked them up in a older collection. They were well labeled, and again, kind of crumbly. So I put them in a Riker mount just to so I didn't have to touch them. I handled them. I got latex gloves and handled them with that, and then just disposed of the latex. But I did have a Geiger counter run over them, and as I recall, it was really just above background.
So you assume you have the label on the back of the box.
I have my personal identification number, if you see there, which
Okay.
corresponds to my catalog, my mineral catalog. So, and I do have, yes, a label that goes with it, but I store it separately because of the nature of being in a box.
Thank you, Patrick.
Very,
Enjoyed your
very-
talk.
Thank you very much.
Yeah.
Very good talk,
you.
Patrick. Very
Very good.
interesting.
My pleasure.